Hello, everybody, and welcome to this PV Magazine webinar, Analysing PV System Safety and the Promise of Optimizers. I'm Bella Peacock, the editor of PV Magazine Australia. Here in my country, Australia, the perceived threat of rooftop solar systems led it to mandate the use of DC isolators. Intended as a safety device to stop the flow of current between panels and inverters, in an emergency, DC isolators in fact ended up posing one of the biggest risks in systems, leading to failures and sometimes even fires. The mandate for DC isolators was removed last year in 2021, following years of outcry and lobbying. And I tell this story to note how adding complexity in electrical systems can become problematic, which is what our speakers will be talking about today. I'm joined by Hannes Knopf, who is responsible for strategic development of standards and committee work at SMA Solar Technology, and Dr. Heribert Schmidt, a senior scientist and fellow at the renowned Fraunhofer Institute for Solar Energy Systems. Dr. Heribert will be examining and presenting evidence on PV system safety before Hannes expands on this and looks at modular level power electronics, or MLPE, which includes technologies like DC optimizers, microinverters, and rapid shutdown devices. These technologies, SMA claim, don't always live up to their hype. Before I hand over to our two speakers, who you can see here, they come to us today from what's thought of as the home of engineering excellence, Germany. I need to do a little bit of housekeeping. So if at any point you can't hear our speakers, please let us know using the Q&A or chat function. We are recording this webinar and you'll be given access to that following the webinar. And finally, please get involved, write questions. We'll finish with a Q&A session, but feel free to send your questions through in the chat function at any point whenever they pop into your head. To preempt the most common question, yes, the slides will be made available. So without further ado, I will hand over to Dr. Heribert Schmidt, and both of our speakers are in Kassel.
Yes, thank you, Bella. So in the beginning, I would like to welcome you all, and I would like to briefly introduce the Fraunhofer Institute for Solar Energy System. It was founded in 1981. It's located in the southwest of Germany, near to Switzerland and to France. And we have two directors, Hans-Martin Henning and Andreas Bett. At the moment, we are roughly 1,400 employees, and the budget in 2021 is about 100 million euros. And that's the introduction of the Institute. And what are the business areas? Only I will show them: photovoltaics, materials, solar cell development, module development, and so on, energy efficient buildings, solar thermal power plants and industrial processes, hydrogen technologies and electrical energy storage. And from my point of view, the last one is the most important one: power electronic grids and smart grids. That's my special field. So I would like to hand over to Hannes. So please.
Thank you, Heribert. Hello, everyone. I'd like to introduce you briefly to the SMA Safe Solar approach. We've been in the business for 40 years. We've got a lot of experience of PV technology development. And one of the core principles for our PV technology is to keep systems lean and simple and robust, and integrate all intelligence inside the inverters. And combine this with extensive testing and quality inspections. We have really reliable offering, very safe technology. And this in combination with hands-on training for customers, for installers, I think should give you a really reliable, safe PV system. But let's dive into the details here. There's been a lot, like Bella mentioned, there's been some press about safety with PV systems, about fires regarding to PV systems. So if you ask the insurance industry, if you look at the statistics by the insurance industry for the main causes of fires, you see that actually roughly a third of all fires were caused by electricity. That means electric devices. Now, let me tell you which devices were the main causes for fires. So dishwashers, dryers, fridges, washing machines, also very importantly, extension cords. PV systems cannot be found here. So why is that? So you actually call an insurance provider and ask them, so what's your failure rate? What's your experience with PV systems? And say, the numbers are so low they're not even collecting the data. It's insignificantly low. So ask somebody else. I asked Fraunhofer. They did a research on this topic, and the result showed that all the fires, all the PV systems they inspected and they were analyzing were super safe. 99.994% have never caused an issue, never caused a fire, to be precise. And only the remainder of 0.006% have ever caused a fire. To be really clear, the big green ball, those are the safe PV systems. They're super safe, they're very safe, and only a small fraction has ever caused a fire. So just have that in perspective. And I'd like to have Herbert actually give you more details about the study, which I think is very exciting, very, very good, important work.
Yes, thank you, Hannes. So we knew that there are very little or only few cases where PV caused fires. But so in the 2010s, roughly, there were a lot of reports in the media dealing with great danger caused by PV systems. I've collected some headlines here. Firefighters under current, solar roofs are dangerous for firefighters, or danger by electric stroke from PV systems. So it was really a campaign, I would say, at this time. And the firefighters were supposed to be hindered when extinguishing fires. And there was one case in a small city close to Cologne where a young firefighter was supposed to be injured by an electric shock in the case of city of Rösrath. So Fraunhofer ISE and TÜV Rheinland then applied for a research project, and this project was performed from 2011 to 2014 to find out the causes of fires in PV systems, how to avoid them, and how to deal with burning PV systems. And besides Fraunhofer ISE and TÜV Rheinland, I myself was heading the project at Fraunhofer ISE. Firefighters and different companies were involved in this project, also insurances, and it was very broadband. The outcome was disseminated in a lot of workshops, presentation at conferences, publications, and a lot of handouts have also been made for the firefighters. There was a lack of information for the firefighters, we found, but I will show later that there is a very clear view of the firefighters how to deal with burning houses with PV systems. So from the beginning, it was clear that we want to prepare a PV safety handbook as a final report. And I'm a little bit proud that this is really a very good handbook. And it has been translated into English. It has been funded by the US Department of Energy. And the translation into Spanish has been funded by the Minister of Energía in Chile. All these documents I've mentioned here are available. You see the links there, and you can find the reports there, the English one, the Spanish one, and in German, all these handouts and the workshop presentations, everything is available there. So I cannot show all the details here, just focus on safety and firefighters. One of the first outcomes was that most of the cases reported in the media, even in the trade press, were fake news. So everybody made it a little bit bigger. Bad news are good news. And even the trade press, you could find such reports. And in the beginning, we looked at all these cases that were reported and looked at the causes, what had really happened. And for example, in the case of Rösrath, which I mentioned, we found there has never been a PV system on the roof, but a solar thermal system. You can see here, we found a photograph that had been taken by a reporter one day after the fire. And on the first look, we saw that's not a PV system, that's a solar thermal system. And the house owner said there has never been a solar PV system on the roof or in the garden. So, and we found this in several cases that the reports were not correct. And at this time, we had more than 1.5 million PV systems in operation in Germany. And we found that no one firefighter has been injured by electric stroke from a PV system. Besides this one, and we reset this number 1 to 0 after we found that there was no PV system on the roof. These results have been confirmed by insurances and trade associations. So in this project, we did a lot of investigations regarding safety of firefighters in case of live PV system. You see some examples here. We measured the current flowing through the water beam with different nozzles. So this fireman is not actually, so it's not a real person here. It's just a dummy, and we measured currents flowing there. We put a dummy into a water bath and measured the current and so on. And we also measured the currents and voltages produced by artificial light, because sometimes during night, firefighters use artificial light to, when they are working, do their work. Okay, so to come to a conclusion, we have also taken rapid shutdown systems into account. Are they helpful for the firefighters? And the firefighters' comments and conclusions were absolutely clear. They said, we know how to deal with energized electrical system, also battery system and so on. We cannot shut down. We know how to deal with energized electrical systems. Second one, as long as rapid shutdown systems are not 100% reliable, we have to handle PV systems with and without ISD as being energized. And this leads to the conclusion, rapid shutdowns are not beneficial for firefighters. This was a very clear statement of the firefighters. And therefore, in Germany, rapid shutdown systems or shutdown systems at all are not mandatory. That's a very clear result of this report. So I would like to hand over to Hannes again.
Thank you, Harry. Yeah, thank you for presenting those results. And I think it's really interesting to learn that firefighters, educated firefighters, came to the conclusion that actually a rapid shutdown has no benefit for them, since it wouldn't be 100% reliable. They wouldn't know in case of an emergency if this rapid shutdown is actually functional, how it's functioning, and so they would treat the system as a live system anyway. So what's the benefit of such a rapid shutdown system at all? Is there a benefit? And I think this is partially answered by a very important sentence, quote, in that study that Harry just presented. And I'd like to read the quote to you. It says, often safety components like fuses, switches, are integrated in the DC part of the PV systems. In the individual case, it must then be always checked whether this measure is really necessary. And then it goes on, each additional component poses the risk of additional contact points and other sources of faults. A sleek system with as few components as possible has the advantage of having fewer points where damage could occur in the system. So more complexity means more points, potential points of failure, higher risk. So if you start adding components, for example, for rapid shutdown, you're actually increasing the risk than reducing the risk. That's a very important takeaway from this study, I think. And let's further dive into this and try to explain what that means and how this actually comes to be. Okay, here basically you see a PV system consisting string inverter PV system consisting of a string of PV modules. The first PV module in the string, you got the module plus the connectors interconnecting it to the next module. So I'll show you the next module. So 2 modules, 2 points of interconnection. 3 PV modules, 3 points of interconnection, and so on. So if you compare this to a PV system using module-level electronics, be it optimizers, rapid shutdown devices, etc., in short, MLPE, you got the following. You got the first PV module. You got the module-level electronics device. This is a little box at the bottom here with lots of electronics inside. And it comes with 2 pairs of extra connectors. So in total, you got 3 points of interconnection. So you add the next PV module, a third PV module, and each time you add the electronics, And just a rough estimate, per module level electronics box, you add roughly 300 electronic components. That means diodes, transistors, resistors, capacitors, and so on. All those little things inside the electronics box. And with the box comes two pairs of connectors. That means 3 points of interconnection in total per PV module. So if you add this up, now let it run for a while to see where this leads to. There's a 10 kilowatt peak system, a 30 kilowatt peak system, 100 kilowatt peak system, 300 kilowatt peak system. It could all go on and on, but I stop it here. And let's look at the results. For a 300 kilowatt peak system, you got roughly 1,000 PV modules. For a string inverter system, you got 1,000 points of interconnection. And those interconnections are done with connectors from the same manufacturer, manufactured most likely the same date, manufacturer actually included with the PV module by the module manufacturer. For the module level electronic system, of course, you go to PV modules with their connectors. You add all the module level electronics. That means you're adding extra connectors, 3 times as many instead of thousands. You got 3,000 point of interconnections. And you're adding all the electronics. And in total, a rough estimate for the 300 kilowatt system, you're adding 300,000 little electronic devices on your roof. On the roof, in an environment where, starting again for some reason. Oh, there we go. Okay, so quick summary before I get to the environmental discussion. You got 3 times the number of DC connectors, as I said. There is the risk of mismatch because the DC connectors which come with the PV module, well, were attached to the PV module by the module manufacturer. Then you've got the manufacturer of the module level electronics. They're adding their DC connectors. Ideally, they would be the same manufacturer, same module. Well, maybe they're not. Then it gets even worse, right? So you're increasing not just the number of connectors or connecting points, you actually adding additional risk by potential mismatch between connectors. You get corrosion, and eventually corrosion leads to bad contact points, and eventually this might lead to sparks, to arcing, and to fire. So again, you're increasing the complexity, you're increasing the risk. And there's a very important technical report out there done by the ISE in 2019, where it talks about the incompatibility of DC connectors in DC applications and PV systems. And there it says, several countries report that problems with DC connectors are a major cause of failure, such as fire hazards in PV systems. Luckily, the numbers are still very low. Let's not change this by adding module level electronics to the PV systems. So keep MLP out. To summarize it, PV systems are super safe. Less is always more in this case. Less complexity means more safety and more lifetime. Keep complexity out. Don't add extra devices which have questionable benefits. They increase the complexity, they increase the risk for potential failures, for potential fires. Now we have a quick poll. Bella, would you want to take over?
Hello, I do indeed. Yes, we've got a quick poll. You'll see that over on the right hand of your screen, everybody, under the polls kind of function. So the poll is open now. And the question is, how does the safety of a PV system compare to other electrical systems? Is it less safe or more safe than most electrical appliances? So everyone, get on there, start voting. We would like to see how well you've been listening. Very well is the outcome. 93% of you were correct. Hannes?
Well, I'm glad that's the outcome. Otherwise, I would have started again to make it really clear what I'm trying to say here.
And we have a second question for you that is going to open. What causes more fires? Are the dryers, dishwashers, extension cords, or PV systems? This one's slightly more complex. We thought we'd ramp it up for you just to test it out. So everyone head on to your polls. Oh, dryers and PV systems. What do you have to say about that? 50-50, it's an even split.
That's interesting to see that as an even split. Well,
oh no, okay,
still keep changing, so maybe those were the first 2 answers.
Yeah, it just had some lag issues. Okay, extension cords, dryers are the leading causes. causes, apparently, according to our audience, dishwashers coming in third, PV systems, we can agree that they are more safe. What is the actual numbers between dryers, dishwashers, and extension cords, Hannes?
I don't remember exactly, but it's in the graphic I showed in the beginning. So it's definitely, those are the top three. And if you remember the picture I had in there with the extension cords where all those things are plugged in together, this is the very risky situation where people just think they can just string them together and add more loads to it. And this actually eventually leads to overloading and overheating and to fires. And this is very risky. And PV systems, so they actually really show up as one of the major causes of fires. And PV systems, they don't even show up in all the statistics that the insurance industry provides.
Perfect. Well, 44% of you were right on the money. And dryers and dishwashers also rated in there. So really don't feel too bad. I will let you go on with your presentation.
Thank you, Bella. So let me get back to the environmental situation. The environmental situation on your roof where your module level electronics will be located. Those little boxes, black boxes, are located behind the PV module on the roof. Remember, for the 300 kilowatt system, that's 300,000 pieces of electronics on your roof exposed to heat, to moisture, to freezing, to temperature cycles. All this is not very good for electronics, so to say. They suffer under those conditions. So one thing an engineer can do to somewhat protect them, at least from moisture, is to fill the housing where the module, while the electronics are located in, to fill that with liquid, some liquid plastic, which then turns into a solid. So you got a solid block of plastic in there where all the electronics is located in. It's questionable how you get this ever apart, but that's how it's the best protected on your roof. But also, I'd like to introduce to a law of physics, the Lusser's law. Basically, it tells you the reliability of a series system of components, which is equal to the product of the reliability of the individual components. It also says that a series system is always weaker than its weakest link, which I was trying to indicate here on the right-hand side. So the formula the engineers are using and applying this law is the total system reliability is always the product. That means the multiplication of the reliabilities of the individual components. Let me give you a bunch of examples. The first example, very simple. You have two components. One has a reliability of 90%. The second has a reliability of 80%. The total system reliability is 72%. Let's look again at the example with the 300,000 electronic components. The first component supposedly has a really high reliability of 99.999%. That's at a second component. So you multiply the reliability of those components, both are super high, you still have a very high reliability of 99.998%. Let's go on with this. Let's look at the example of 300,000 components. So you got 99.999% to the power of 300,000, which gives you 5% reliability. So if your numbers go up, the reliability drops drastically. And though that's the theory, let's look at field data. And interesting enough, a Swiss institute, the BFH, Berner Fachhochschule, just recently published a new report, a study, actually a survey they did with installers and PV system owners in Switzerland. And they've got roughly 1,200, somewhat more than 1,200 participants in that survey. And I'd like to show you the results. So basically, what you see here is the survival probability, Überlebenswahrscheinlichkeit, of different types of PV systems. One PV system is based on string inverter technology, and the other PV system type is based on inverters with module level electronics. For example, optimizers in this case. And what you see is PV systems with optimizers, they drop below 75% survival probability only after 6 years. PV systems without module level electronics, without optimizers, they actually stay above 75% survival probability for 12 years. I think that's a very interesting outcome, which reflects actually what I was just explaining in theory by Lasser's law. Just a little note that shaded area indicates the interval of, I think, of confidence, they call it, which is basically derived from the number of systems which were part of the survey, which of course gets lower over the years because there are more and more PV systems added now to that pool of total systems being installed. So the takeaway here is very important. So the survival probability of systems without MLP is twice as high or drops half as fast as for systems with MLP. Now, to make PV systems even safer, we at SMA decided to start adding our arc fault circuit interruption, we call it arc fix, to all of our string inverters. Therefore, we're successfully preventing arcs in a PV system and successfully preventing fires in a PV system. And again, we're not adding any electronic devices to the system. We are not adding complexity. We're actually integrating this functionality in our string inverters. It's all integrated, no extra connection points, no extra complexity. And if you draw this as a graph, basically of the evolution of PV system safety over the last decades, so you continuously kept increasing, adding safety functions, increasing the PV system reliability and PV system safety. And if you now start adding arc fix, the safety goes even further up. And I also try to indicate with that red arrow where the safety might be heading if you start adding MLP to the system, at least based on the data and the reports and the studies I'm presenting here. Now, let's get to the final point, which is really also close to my heart. Actually, the reason why I decided to pursue a career in power electronics, and in particular, a career in the renewable energy systems. It's to keep our environment clean, to be responsible with our resources, to have renewable energy supplies. Let's look back at the 300 kilowatt system I had as an example first. We've got 300,000 additional electronic components. One of the major suppliers of optimizers stated in their 21 annual report that they have shipped so far 84 million optimizers. 84 million optimizers, that's roughly, if you look at the data sheet of those things, more than 80 million kilograms of electronics. That's more than 100,000 cubic meter of electronics. Just to give some sense of those volumes, of those amounts, this equals to more than 700 loads of Boeing 747 aircraft, cargo aircraft, shown on the right-hand side. So this is a lot of electronics. And as I said, this is all potted. So this is all encased in liquid, well, then solid plastic inside those black little boxes. It's questionable, how do we ever get this apart? Or if it actually lands in the landfill, ends up in the landfill eventually. And I don't know if that's really the concept we should pursue as a renewable, clean energy. We, with SMA, we keep our systems clean and smart, and also the energy and the environment clean and friendly. We have another poll here. Bella.
I'm back with more poll questions. Okay, again, we'll be looking at how well everybody's been listening. So what makes a PV system safe? That's the question you're answering. Is it low complexity? For instance, a low number of devices and connectors? Is it B, quality components, C, good workmanship, or D, optimizers and rapid shutdown system? Is that the question we're answering? Are we answering how many? Well, my computer came up with the first one. Maybe we're answering what makes a PV system safe. I gave you a little sneak preview of the next question just for you guys to ruminate on. But what we're actually answering is, how much do rapid shutdown devices improve system safety? Is it a lot, a bit, not at all, or decrease safety? So we're kind of on almost an even split. Not quite. I wonder if these numbers will update themselves. But at the moment, some people are still saying that it improve safety a lot, Hannes.
That's interesting. I was hoping for the numbers actually to update a little more, but if that's the final result, I'm a little surprised. So I wonder how a rapid shutdown system would really improve system safety. As I said, you're adding complexity, you're adding risk, you're adding actual additional points, potential points for failure and fires. So I don't see really how you would add and improve the system safety.
And it's kind of a bit similar to what I was trying to outline in the introduction. I mean, the DC isolators in Australia ended up to be kind of chaotic, and it was really widely celebrated as a huge win for the industry when that mandate was taken away at the end of last year.
Let's use that as an opportunity really to elaborate on this topic of safety. So adding electronics to the roof, as I said, it adds complexity. It adds potential points for failure, potential fires. That means the firefighters might have to come more frequently. As we learned, firefighters must not rely on the safety of rapid shutdown. So what do they end up with? They end up with more frequent interaction with PV systems. They cannot rely on the proper rapid shutdown because it's questionable that this devices actually still work after 10 or 15 or 20 years, how they work. So what they're encountering more fires with PV systems, not anybody would want to like. Also considering installers, as we learned, those systems are more likely for failures. That means more maintenance, more hours spent on the roof replacing those devices, taking PV modules off, replacing the electronics behind, putting the PV modules back on. Any hour you spend on the roof, working on the roof, is very tiresome. It's also very, very dangerous. Actually, many roofers get hurt and some even killed by slips and falls on the roof. Same as installers, not by electricity or anything, but just by the situation on the roof. So you want to keep that time on the roof as little as possible, not add time on the roof. So with the module-level electronics, you're adding time on the roof, you're increasing not only the risk for firefighters, but also for the installers doing those installations. So that is what I've learned from all the studies I've been looking into.
Yeah, so I mean, the gist here is actually, I mean, according to Johannes, they're kind of decreasing or definitely not improving safety. At least kind of that's what some of the data you've presented shows. And then we're going to go to the question that I sneak previewed before. What makes a PV system safe? Is it low complexity, quality components, good workmanship, or optimizers and rapid shutdown? More points. We've got 65% saying low complexity, which Hannes, I believe, is your position also.
That's correct.
Quality components probably don't hurt at all. And good workmanship also probably does help. Do you have anything you want to add there?
Well, I think good workmanship is very crucial. If a system gets slapped together by some, I don't want to use any funny terms, but it should be always qualified workers doing the installations, since we have a system that's supposed to be running at least 20 years or longer. You have high power, you have high voltage up there, so you should have good qualified workmanship to do the installation. That really should come up much higher here than it has been. I wonder, Bella, are people able to basically say yes to multiple of those questions or multiple of the options, or do they only have the choice for one option?
That's a very good question, Hannes. We're not allowed to take part in the polls because we're presenters. So I would love to give you a qualified answer.
Got three good answers to this question, right? So what makes it safer? It's quality components, it's good workmanship, and it keep complexity low. That would be the right answer. All three of them.
Okay.
Thanks.
Do you want to go on, Hannes, and then we can readdress these questions once we come to the Q&A section shortly?
Right. So let me show you another slide, and that's addressing some concerns you guys might have listening, or some idea you might have of potential benefits of module-level electronics. And that's referring back to a presentation I did, I think a year or two ago, regarding the yield and energy you generate with a PV system. And back then we were actually looking into a study done by a university in Denmark, which came with the results that for systems well, comparing string inverters with module-level electronic systems, string inverter systems in general had higher yields, or at least equal yields, in comparison with systems of module-level electronics. Even in slightly to medium shaded situation, the PV systems with string inverters would perform better. And in particular, we were reviewing back then our performance with shade fix, and that came out very well. And we found that only for very heavily shaded systems, shown here on the right-hand side, there's a slight plus in the total annual yield of a system compared with a string inverter system. That's due to the fact that with the heavy shading, there are some occasional situation where an optimizer has some benefits. But keep in mind, if you have heavy shading throughout the day, this makes the economics of such a system very questionable, because if there's no sun on your system, there will be not much energy. Just a little 2% extra by an optimizer with a system that yields very little energy still doesn't make this system economical. So let's get to the final conclusion of today's presentation. In general, we've learned that PV systems are very safe. PV systems are been there in the market 20, 30 years, and the insurance companies have very little to no data to talk about any issues regarding safety. SMA ArcFix, which is now being introduced with all our string inverters, makes PV systems even safer, more reliable. Less is always more. Less complexity means more safety, less points for failures. You need to focus on a lean system design, ideally integrate all functionality into one component into the inverter. Do not add extra devices onto your roof, which add extra contact points, extra points for failure and risk. And with SMA string inverters, we've got all the integrated functionality that you need. We've got maximum safety with ArcFix. You get maximum yield with shade fix, and you got maximum lifetime just by design. Thank you very much. We've got some time for questions and answer now. I'll give it back to Bella.
Thank you so much. So, Haribert, are you going to come back in?
Yep.
Oh, perfect.
Here I am.
Let's just start out by asking, I've got some kind of technical questions. On that presentation, Hannes, you had 3 connection points with MLPE. One of the questioners says he thought that there was only 2 connection points. Why is it that there was 3 demonstrated on there? That's
okay. I'll go back to that slide then. It's the easiest to discuss this. I think here it is. I guess I need to start the presentation here. Okay. So for a system with string inverters, you've got one interconnection point between each module. So each module basically comes within one interconnection point with the module next to it. Here on the top. In the bottom of the system with MLPE, you're adding the optimizer or the rapid shutdown device to the PV module. That means you have those 2 interconnection points here at the bottom. I don't know if you see the mouse, but you got the 2 interconnection points at the bottom interconnecting the optimizer to the PV module. And then, of course, you have to interconnect that to the second module next to it. So you got 3 points of interconnection per module instead of 1 point of interconnection per module. I hope this answers the question.
that hopefully does. And one of our viewers is also saying that presentation was quite theoretical. What is the real fire danger caused by MLPE? Is there data to support these claims?
Yeah, it's really hard to get data. As I said, the failure rate is super low in general for PV systems, but you can of course compare PV systems with MLPE and PV systems without MLPE, and there are several very well research documents, such as the study from Fraunhofer or the ISE document I was quoting. Also, the experience from Australia, you reported that adding complexity for example, rapid shutdown devices does not do any good. Actually, it increased the risk level, the failure rates. So I think that's the data we have. That's the facts we have.
Okay. Do you know what percentage of the worldwide market is currently installing MLPE systems?
Could you repeat the question, please?
Do you know what percentage of the worldwide market is installing systems with MLPE?
I don't know, unfortunately. Yeah. Good question, though. Yeah.
Perfect. We had another question, and this is there's a few different iterations of this. What are the benefits then of MLPE? And Heribert, this one might be better suited for you. Does it offer any safety, any additional safety for firemen in the cause of a fire incident?
That's what the manufacturers of such systems say, but no system is 100% reliable. And so the conclusion of the firefighters we had in our projects and also in another project, they said as long as it is not 100% reliable, we have to treat the system as being energized. And so what? Why should we have these additional systems if they are not 100% reliable? So this a simple answer to this question. In principle, if such a system would work 100% reliable, it would be helpful, but it is not 100% reliable.
So instead of adding safety, actually it increases the risk. It does not have any benefit or noteworthy benefits regarding yield, and neither in lifetime. So I don't see much benefit, honestly.
Okay. We also had a question about whether ArcFix from SMA could be considered a replacement to rapid shutdown systems or rapid shutdown devices, sorry.
Okay, ArcFix is not replacing rapid shutdown. It's actually a totally different function. It detects potential arcs in the systems, suppresses the arcs, so arcs cannot develop. And so that's totally different from rapid shutdown. Rapid shutdown has nothing to do with arcs. So it's an alternative which makes PV systems safer versus module-level electronics, which has some doubtful impact on safety, as I said.
Interesting. Thanks for clarifying. Coming back to this question on kind of data around MLPE and the safety of that, is the fact that there's not much data, is it because PV system technology and installation is fairly recent, and there just hasn't been much time to gather that data, or is there another reason that data is missing?
Well, there is data. As I said, there is no data of failures at insurance companies, but the research that Fraunhofer did came up with this data. So maybe how about you want to say 2 words to that?
Yeah, we did not look at reliability. We only looked at safety aspects in this firefighters project. And so we found that in Germany at this time, we had 1.5 million systems operating. And there was this number that Hannes already showed, very, very few systems that caused a fire. There were houses that burned, like houses burn if a candle falls or something, that had a PV system on the roof. But in this case, there was a PV system, but it did not cause a fire. So you have to distinguish between these cases. And there were very, very few cases where actually the PV system caused the fire. Only a few houses. So I don't have the numbers in my head at the moment, but everything is mentioned in the report. So maybe 20 houses that burned down with PV system, and only some of them, the fire was caused by the PV system.
Interesting. We've got another question. Optimizers can detect and locate PV panel failures. What do you think about that? Hannes or
that's one of the points why people supposedly buy optimizers. But I think what's important is the outcome of the study done by the Swiss Institute, by BFH, which actually showed a lifetime of a PV system gets cut in half by adding optimizers. So you try and detect failures of the module, but you're adding additional failures by the optimizers. So There are other ways to detect PV module failures just by the energy yield, for example, or by looking at a total curve of the string voltage versus current, which will also show you module failures. There's no need to actually add module level electronics to detect any failures. You're actually adding failures instead.
Interesting. I've got some questions coming in about yield, but I did want to ask, first off, why would insurance companies require MLPE and rapid shutdown systems if it's not doing anything for safety of the PV system? And the same goes for requirements of standards in the NEC in the US.
Very good question. Well, you
So
answer
maybe
this?
you can
I'll
add this few slides that I had.
We'll probably get to this later, but yeah.
Okay.
So let's start with the insurance companies. There's just a few insurance companies I've heard of asking for module level rapid shutdown, and I wonder if they know actually all the facts. They probably do not know the facts that's being presented by Fraunhofer ISE. They have not seen the studies which I presented today. So if any insurance companies or anybody working for an insurance company is listening today, please feel free to contact us. I'm happy to sit down together, to look through those things, have a discussion together. I think that's a very good point to really start looking at the facts instead of just listening to rumors. And regarding the NEC, National Electric Code in the United States, which made it more or less mandatory to install module level rapid shutdown, I think it's also a case of misinformation of the firefighters who happen to write the local code for the installation requirements in the United States.
Okay. Coming back to this kind of yield analysis question, another person asked, did you have yield analysis for PV systems with MLPE optimizers versus without?
Yes. We had actually, the study in Denmark, which was done by the University in Denmark, had 3 systems side by side. There was a system with optimizers, which was basically designed as a system with inverters and optimizers, which always must run together. Then there was a second system with an SMA inverter and optimizers, which were added to a regular string inverter. And then there was a system, just a regular SMA string inverter with shade fix. And the outcome was that in most cases, the shade fix system with just a regular string inverter, modern shade fix technology, without any MLPE, would outperform the other systems.
Okay. We've got a few questions about ArcFix, so maybe I'll try and ask them together. One person asked, is ArcFix automatically included in the power converters? Is an F/W update enough? I'm not sure what F/W means, but hopefully you do.
F+W?
F/W. FW update enough. I'm not sure.
Firmware, probably. Okay.
Maybe the answer the question.
I think that's firmware. So firmware
okay.
is sort of hardware, so software update.
Okay.
It's not, ArcFix is not available by software update. It has to be included in the inverter basically from the factory here. But we are starting, or we have started already adding this, integrating this in our string inverters, and we'll be converting all our string inverters to include this functionality step by step in the future. So we've had this for the United States because it's mandatory there for more than a decade, and we were the first ones to offer that in the United States in a certified product. So we've got a lot of experience engineering, designing arc fault detection systems, including this ArcFix in our series products there, and now we're introducing this in our series products here for the rest of the world as well.
Okay, and another question, just staying on the topic of ArcFix. One question asked, can I say that your ArcFix feature, so SMA's ArcFix feature, has similar arc extinguishing design built in circuit breaker without interrupting shoots or the likes?
I'm not sure if I clearly understood the question. Could you try to read again or repeat it again?
So the feature, does it have similar arc extinguishing design to a circuit breaker without interrupting shoots?
Interrupting shoots. Okay, so it's very since a circuit breaker is a mechanical system, it works very differently from our ArcFix function, which is based on a software detection and then power electronics devices turning off the current. So it works differently. I don't know how more you could compare it, but it works differently. I think that's the easiest answer, the clearest answer.
That does sound like the clearest answer.
It works really reliably. So the testing, the standard testing for ArcFix or for arc fault circuit interrupter is very, very demanding. So it's not easy to fulfill those requirements. That's very clear.
Perfect. And Heribert, this next one's for you. In the PV Fire Safety Handbook, the relative risk of electrocution for firefighters is said to be high. This seems to be in contrast with the results communicated. Can Heribert, or maybe elaborate on the risks associated with opening the roof, flooding the perimeter, or walking on the roof? These actions are said to pose a high risk of electrocution.
So the question was if there is a high risk if the PV system is still energized.
Yeah, the question is, about basically this kind of contrast between.
I'm not a firefighter, but we had firefighters in our project, and so I can only tell you what they told us, and I've have learned a lot of them from them. They said that for us it is no problem to handle PV systems that are energized. So that's simply information, and they do it. So there's no house in Germany that burned down because the fireman did not go onto the roof or so, and not one fireman was injured until now. So these are the clear results.
I try to add a little bit to this. As Herbert said, a PV system or a rapid shutdown system, to be precise, is never ever 100% reliable. So a firefighter will always have to treat it as live, as energized. Also, I think a so-called rapid shutdown, I call it so-called because it's neither rapid nor shutdown. Actually, it reduces the voltage in the time of 30 seconds. So it's not immediately off, it's not rapid, and then it's not off completely. So it actually, the term rapid shutdown kind of promotes a false sense of safety. A system is not fully shut down even though the rapid shutdown has been pressed. The voltage is still present behind the PV modules. So if a firefighter is misled into thinking this system is safe and starts hacking into the PV modules, he'll encounter the open circuit voltage of that module because that's still there as the sun is still shining or the light is still on the PV module. And then he'll be most likely caught very surprised because he has been misled thinking the system is off, has been shut down, but it's not. The voltage is still behind the PV module. So it'll be touching the broken pieces. Be surprised. I don't know how you'll react surprised on a roof which is on fire. Maybe you jump just a little bit and the roof is slopey. So I talked about falls, slips on roofs. I don't think firemen like big surprises when they think the thing is off. So I'd rather don't touch it all. Don't touch it at all.
This is another question. So from one of the viewers, 0.006, which does sound like a small percentage, is in fact not that small of a number when you think about how many millions of systems there are installed on roofs. How can you state that the rapid shutdown devices are not required?
Because rapid shutdown devices are not making systems any safer. So this number is likely to go up if you start rapid shutdown devices.
Okay, coming back to the question of yield analysis, one of the questioners asked, are those yield analysis, is that yield analysis conducted in Denmark that you referred to, Hannes, actually compared to the optimizer-based system based on one specific model to SMA string inverter-based systems, or was it the study, was the study covering as many different makes as possible?
Well, there's always a limit to the number of makes, right? There's a limit in size and space available and of course, funding available for a study. And the comparison was done with regularly designed systems, two systems comparing actually two SMA models, one with MLPE or optimizers, the other one without optimizers. And the other one was, as I said, a system which was a system which always does consist of optimizers and inverters in a combination. It would not run with outside this type of combination. I hope this answers the question. But there's so many models and makes and manufacturers of, in particular, inverters, but also of optimizers by now. There's never a way to compare all of them, right? It's just limitless, endless, yeah, I would say.
So in research, we must have a defined question, I guess. To come back to ArcFix, Hannes, are there any tests or certificates applicable to ArcFix systems? Which certification has been obtained for ArcFix in the US?
Yeah, there's a UL 1699B, I think it's called. There's the latest edition of it, and so we've certified our ArcFix to that edition. Also, there's a new standard coming, ISE standard. I think it's still in a draft version, but it's close to be done, what I was told. And we also certified to this. Actually, we've done all our testing to this standard, so we can also claim that we're fulfilling the new upcoming ISE standard, as well as the already existing latest UL standard.
And probably one of the final questions, how does ShadeFix increase the output for an unshaded PV system? Does it add components and complexity to the PV system? And if so, is it worth the additional safety risks?
Okay, ShadeFix, as it is now extra device, it's integrated as a smart function inside the inverter. It's just software. It's not adding complexity and is not adding a safety risk. For an unshaded system, basically, the system would perform equally with or without ShadeFix, I would guess. But you always, let's say in the early morning, on the evening hours, you have an occasional shade on almost any system. And so ShadeFix will always be better off if you have a ShadeFix system than an inverter without ShadeFix. But for unshaded system, I would expect the difference to be really, really small.
And one viewer has also asked why SMA previously sold inverters with a Tigo optimizer. And yeah, well, I'll just ask that.
No, very good question. I actually was almost expecting this question to actually be asked. So yes, in the past we sold optimizers, or actually distributed optimizers, because customers were demanding them, they were asking for them. But since we've learned so much about optimizers, not only today, but also throughout the last years, we honestly do not see any benefit for our customers buying optimizers. And that's why we discontinued offering optimizers.
And do you have any data to show that if the systems with those optimizers failed more often, or?
Yeah, of course. That's the study I mentioned. It's the preliminary results of the study done in Switzerland. I'll try to jump to it quickly again. That'd be BFH, Berner Fachhochschule. Here we go. Where we see, you can see it here. So basically, you see the survival probability of PV systems without optimizers is twice as high in the same time frame as for PV systems with optimizers. So in other words, optimizers and systems with optimizers fail more frequently than systems without. And that's field data. That's a survey done by a Swiss institute.
And just one final quick question. Is the rapid shutdown not a recommendation in Germany and throughout Europe anymore?
There never has been a recommendation. Maybe Herbert, you can say a word or two to it. There's actually Anwendungsregel,
yes,
which tells you how to do it, right? If you want to do it. So do we want to switch to it?
Yeah.
Okay.
You can.
I'll try if I get there. Let's see.
Two more slides or three more slides.
Yeah,
so it's a German Anwendungsregel, VDE. And it was the same reason as we had before, all this fake news in the papers. And the ministers, the interior ministers of the German states, which are responsible for firefights, they asked the German Commission for Electricity, the DKE, to develop a norm for rapid shutdown systems. And I was one of the experts that had been working on this Anwendungsregel together with a lot of other people, also firefighters. And we discussed a lot of possibilities how to realize such a systems. Only 3 examples here. The left one shows a system that puts a code on the PV models, and after that they call it an artificial night. The PV module will be de-energized. The second in the middle shows a switch, an automatic switch that depends on heat. So if it is burning, some material weaks, and so it opens the circuit, or you can even open it with a hammer. The firefighter can knock with a hammer on it and open the circuit. The third one shows a module level disconnect system that is close to the rapid shutdown systems we know today. And from the point of view of the firefighters, the 2 first ones, they are impossible. And in the third case, they said, it's I come back to this again, it's not reliable. So second one. I already showed these 3 comments of the firefighters. We know how to deal with energized electrical systems. And if it is not 100% reliable, we do not have an advantage. So rapid shutdown systems are not beneficial for firefighters. This was a clear answer. And the consequence was that the Anwendungsregel definitely does not prescribe rapid shutdown systems. They are optional. If you want to install them in Germany, you may install them, but they are not mandatory. But if you install such a system, you have to fulfill some fundamental technical requirements, and these fundamental technical requirements have been defined in the Anwendungsregel. So once again, clearly, there is not a must for such a rapid shutdown system in Germany.
Thank you.
Oh, thank you so much to both of you speakers, Hannes Knopp from SMA and Dr. Heribert Schmidt. And thank you all at home for your questions and participation. I am really sorry if we didn't get to your question. We literally got hundreds. And so it wasn't out of, it was just because we had a lack of time and we already spent 20 minutes on the Q&A. So thank you for your questions and your interest. Before we go, I just wanted to remind everyone you can pick up your copy of PV Magazine's International Latest Edition, which is pictured here. You can also read our current and trending news, like my piece on the current electricity system crisis in Australia and the scaremongering that it's producing. And also that New South Wales, our most populous state, is making some massive renewable energy investments off the back of this crisis. There's also some more great webinars coming up, including algorithms for solar tracker optimization under adverse conditions. We had some questions today about trackers, so that might be of interest. And Chasing the Sun, advanced analysis for innovative PV materials. So if you register for these, even if they're held at a time that isn't really working for you, you'll be able to see the recordings afterwards. You'll also receive a short survey when you click out of this webinar, and we're always looking to improve. So please, your feedback is always really welcome. There will be a recording of this webinar and an email link with the slides. Thank you all so much for joining us. And thank you again, Hannes and Heribert. Have a great day. Farewell.
Thank you, Bella.
Bye-bye.
Bye.
Bye, everyone.